Okay, can you see it and hear me?
Yep, you're good.
Okay, good. I'm gonna put my actual glasses on now so I can see what's happening. All right, so our last lesson, lesson 31, is on motion graphs, and we're learning to interpret motion graphs using properties of slope, okay? So these are common EQAO questions. There's usually always one on every EQAO test. And they're pretty straightforward. We'll go through a bunch of examples together. We're going to do the whole lesson now, and then you'll do the whole practice, and then we'll be done. Well, you'll have your one little assignment to do at the end. Okay, so the first question, dogs versus cats. The Bryant Bulldogs basketball team takes the bus to play the Jordan High Thundercats. So that's all it says there, and then it says complete the table. So all the information we need should be on the graph. So let's do our axes first. So always look and see what your horizontal one represents. It's the time in minutes. And then always look and see what your vertical axis represents. It's the distance from school, okay, in kilometers. So if you're looking at this graph and you're trying to think about what's happening here, the sentence really helps too. The Bryant Bulldogs basketball team takes the bus to play the Jordan High Thundercats. So they start at their school. The Bryant Bulldogs start at their school. So here they're 0 kilometers away from their school down here. And then they're driving. They're getting like 5 kilometers away from their school, 10, 15, up to 25 kilometers away from their school. And then all of a sudden they stay at 25 kilometers away from their school for quite a while, because this is time down here. So that must be when they're playing the basketball game. And then all of a sudden they start getting closer. So instead of being 25 kilometers away from their school, say over here, they're 17.5 kilometers away from their school. And they keep getting closer and closer to the school till, again, they're 0 kilometers away from their school. Because if we're looking over at what distance they are at 180, it's 0 kilometers. So this is going back to their school. Okay, so that's what's happening in the graph there. And then to complete the table, we have to take information from the graph. So for part A of the graph, which is this chunk here, we want to know the distance they traveled in kilometers. So they started off at 0 kilometers away from their school, and they ended up in part A being 25 kilometers away from their school, which means they traveled 25 kilometers. How long did it take them to do that? So basically, we're doing a rise and a run here. So we just did the rise, and that was 25 kilometers. So this distance column is our rise column. And then the run, let me just use a different color there. For this one is, you can see it's from 0 to 30 minutes, so it's 30 minutes. Or you can realize that the scale is 10 minutes, so 10, 20, 30 minutes. So this is our run. Usually there's this direction column, and that wants you to interpret the direction you're going compared to the start. So if we start at the home school, then we're going towards Jordan High, okay? Or we can say away from our home school, okay? Either one of those will be fine. So our direction, we're going away from our school. And then the speed is distance over time. It's a rate of change, which is really important to know. Speed is a rate of change. So we use the formula rate of change or slope is rise over run, and that's going to give us the speed. So we've got our rise, it's 25 kilometers. We've got our run, it's 30 minutes. We have to fit our calculations into a chart, so write as small as you can while still getting your point across. And then you notice often they'll tell you in the chart what units to use for your speed. So it says in kilometers per minute, which isn't a common unit that you would use, but that's what they tell you to use. So I see 0.83333. I'd at least probably write approximately, so a dot above my equal sign, 0.83 kilometers per minute or 833. I wouldn't just leave it at 0.8 because it's not exactly 0.8. And I do have minute written on here, although it's, there it is, minute, kilometers per minute. Okay, so for the next part B, kind of go over this in a different color. This is part B here. You can see that it doesn't rise up at all. So the rise is 0 kilometers, or the distance, and which also means the distance traveled is 0 kilometers, because I start off in section B being 25 kilometers away from, say, Bryant High. But at the end of section B, I'm still just 25 kilometers away from Bryant High School, where I started, okay? Or you can think of the rise as 0, is another good way to think of it. But how long? The time isn't 0. We were there from 30 minutes to 120 minutes. So you can either do 120 minus 30, and that gives you 90, or you can count them. We know it's by tens, 10, 20, 30, 40, 50, 60, 70, 80, 90 minutes. Direction. So for direction, we're not going towards our school or away from our school, we're stopped. So another reason they put that column in is because they want you to realize that on a flat line, on a distance time graph, that indicates being stopped, or a horizontal, flat line, you're stopped. So that's important for you to understand or be able to interpret your distance time graph properly. And if you're stopped, your speed is going to automatically be 0 kilometers per minute. But you can see if I did rise 0 divided by 90, I'll just show you that that turns out to be 0. Okay, so if you do rise 0 over run 90, you get 0. But you also know whenever you have a flat line there, your speed is equal to 0, whatever the units, in this case it's kilometers per minute. But anytime you see a flat stretch on a distance time graph, it means that your speed is 0. All right, and then for the last part, C here, we want to know our rise. So this time we start at 25 kilometers and by the end we're at 0. So our rise is, and this is a negative slope. So we could say that our rise is negative 25 kilometers. And our run is 10, 20, 30, 40, 50, 60 minutes. And our direction, this time we're going back to our school or towards our school. And if we use rise over run, we would get approximately negative 0.411 or 4.2 if the 6 rounds up, depending on how many decimal places they want, kilometers per minute. But one thing we don't talk about is having a negative speed. So really it's 0.42 kilometers per minute towards our school, okay? So especially on multiple choice questions on EQAO, you'll find they never quote a negative speed. They'll always say that speed is positive, okay, which makes sense because if you see a negative speed, you might think you're moving backwards, you're driving backwards, but we're not, we're just driving towards where we started from. So they'll always write speeds positive, and that's why they have this direction column. So really with speed, even though you realize it's a negative slope, which is a really good thing, you don't have to have negatives in your calculation. You just have to fill this direction part out properly, okay? And then it says describe the trip the team took. So they always throw that question in there to make sure you understand what's happening. So I usually just do part A and then do like a little arrow. Team drives to Jordan High. And then for part B, they play basketball. Oops. And then for part C, they drive back to Bryant High. And that shows that you have a good understanding of what actually is happening in that motion graph. Okay, different multiple choice questions they might ask is, did they drive faster on the way there or faster on the way back? Okay, and by how much? So if you know the speed for each part, you can say they drove faster in part A and then subtract them to find out by how much. And then if you look at the picture, you can see that in part A, it's steeper than part C. So you can see that you would expect that this was faster than this. So that's kind of the basics of a distance time question or a motion graph question. We'll go on to our next one. So look for clues in the question. A student is walking to school from home. So going to school from home. The distance is measured from home in meters. And then always read your axes. So our horizontal axis is time in minutes, and it says time spent walking. And our vertical axis is distance in meters, and this is your distance from school. What? Yeah, no. Sorry. This should say distance from home. Change that. Because the student is walking to school from home. So they start off at home. So this 0, 0 means there's 0 meters, 0 meters from home at time 0 minutes. Make sure you change that to home. Okay, so then we've got this whole big chart to fill out, all the different sections. So for part A, they want to know the distance traveled. So I'm going to look at my rise here in part A. There's my rate triangle. And my scale is 50 meters, so 50, 150, 200 meters. And the time by ones for minutes, 3 minutes. Direction, so you can either say away from home or towards school, they're both correct, okay? I'll write towards school. As long as it makes sense and it's what's happening, you're good. And then the speed in meters per minute, so again, this is your rise column. Vertical. This is your run column, horizontal. And you always do rise over run to get the speed, which is your rate. So it's going to be 200 meters divided by 3 minutes. $66.7 meters per minute. Okay, for part B. Okay, part B, I'm going to put a little star beside. This is what messes people up often in one of these questions. Okay, so for part B, we don't start at 0 anymore. We're starting at 200 meters. So when I'm drawing in my rate triangle, it's going across from where I just finished part A and move into part B. So that's what my triangle looks like. And then I remember my scale is 50, or you can say I went from 200 up to 800, and that's a quick way to get 600 meters. If I want to double check, then I'm going to count by 50s, 50, 100, 50, 200, 50, 300, 50, 400, 50, 500, 50, 600. And then I know I'm counting by ones for my run. So 1, 2, 3, 4, 5 minutes. And I'm still going towards school. It's steeper though, so I'm going faster, but I'm still going towards school. And this time, to get my speed, it's 600 meters divided by 5 minutes. Actually, I think that's going to work out without an approximately. 600 divided by 5. Yeah, exactly. 120 meters per minute. So remember, for part B, your rate triangle doesn't go right to the bottom. Okay, that's the biggest mistake I think people make in this on motion graphs. Then for part C, it's flat. So there's no rise. So the rise is 0 meters. But the run won't be 0. I still have starting at 8 minutes and then going to 10 minutes. So my run is 2 minutes. So I'm stopped for 2 minutes, maybe at a light or something. I could be stopped at a stoplight for 2 minutes. And then I know that if it's a flat line segment, it's stopped. So you're not moving towards school or back home. And then you know that it's flat, so you know your speed is 0 meters per minute. You don't have to do a calculation. And then for D, you can see we've got this negative slope. So we took a little detour. Maybe we had to go back because we dropped something, or someone called us from that was behind us, and we went back to walk the rest of the way with them. Who knows what happened, but we went backwards a bit towards home. So again, this doesn't go all the way down to 0, so it rises by 50s. 50, 150, so 150 meters. You can put negative if you want, but remember, when we're talking about speeds, you don't need to. The distance traveled, you wouldn't say the distance traveled is negative 150 meters, you'd say it's 150 meters, okay? And then how long did it take you to cover that 150 meters? 2 minutes. And the direction, back to home, toward home. We didn't get home, back towards home. And then our speed is going to be 150 rise over run, so 150 meters divided by 2 minutes, which is 75 meters per minute. And then for part E, again, we're going to make our rate triangle. So the rise, we go 50, 100, 52, 53, 50, so 350. See if that makes sense. Yep. Oh no, 650 to 1,000. Yes, is 350. So that's right. And then our run, we go by 1. So 1, 2, 3, 4, 5, 6, 7, 8 minutes. And we're going towards, well, getting to school, I think, right? So towards school. Oops, you can't see that. Bad. 350 meters was our rise. 8 minutes was our run. We went towards school. And then it's going to be 350 meters divided by 8 minutes. Is 43.75 meters per minute. Okay, so this time the additional question wasn't to explain what happened in each part. It's how far from home is the school? So assuming she started at, or the student started at home and ended up at school, that would mean if we read across in the distance, school was 1,000 meters from home. So come down here. How far from home is the school? 1,000 meters. Okay. And there should be lots of things you can check from the graph. Like your steepest part should be your, so part B looks steepest to me. It should be our highest speed, and it is. Okay. We should always check that the flat parts, we have 0 for speed. Make sure you have units everywhere in your chart. Make sure you draw on your rate triangle so you're not tempted to start from the bottom each time, okay? So the only one that started from the bottom this time was the green one. The blue rate triangle, the yellow one, and the pink one all started from somewhere else in the graph. Not right from the bottom. And then an important thing, one of the common misunderstandings people have is they think you're going up a hill, then up a steeper hill, then walking along a flat road, then down a hill, then up a hill. That's not what's happening. Okay, so get those, don't think about that as what's happening. Okay, next question. The graph represents Tyler's walk. Okay, so again, we'll always check the axes first. This one is time in seconds. And this is distance from a motion sensor in meters. Distance from a motion sensor in meters. And we don't start right from 0. we start up here 2 meters away from the motion sensor. So the motion sensor is down here at the bottom. This is where our motion sensor is. Because this axis is the distance we are from the motion sensor. So Tyler's starting 2 meters away from the motion sensor. And for the first half a second, because this is 0.5, he's just stopped there, right? Probably asking, is it on? Something like that. And then here, if we read the question, it says, with what speed does Tyler walk towards the motion sensor? And then with what speed does Tyler walk away from the motion sensor? So remember, the motion sensor is down here. So here, he's getting further away from the motion sensor. He started 2 meters away and he ends up 4 meters away. Here he starts off 4 meters away and ends up only 1 meter away. So here he's walking towards it. Okay. So when this EQAO question was on, a lot of people got those backwards. So it's really important you read the question carefully and the axes, and that you realize that the motion sensor was here if this axis represents your distance from the motion sensor. So now that I know towards is this section, I'm going to set my rate triangle up here. So here's my rate triangle. So each square is worth 0.5, or every 2 is worth 1. So 1, 2, 3 meters is my rise. And my run, each one's worth a half as well. So this is 1.5 seconds. So speed, remember we don't have negative speed. So even though I know that's a negative slope, what it really means is Tyler's moving or walking towards the motion sensor. So my rate is going to be the rise over the run. The rise is 3 meters. The run is 1.5 seconds, which is, if you divide that on your calculator, it should be 2 meters per second. And then you should have a statement. Tyler walks towards the motion sensor at 2 meters per second. You've answered the question nicely. So interpreting which part of the graph was which was the hugest part of the question. The calculations from the rate triangles, we should all be pretty good at by now. So for part B, we want to know how fast he walks away from the motion sensor. So I'm going to set up a rate triangle again for the away part. So every 2 squares is 1 here. So 1, 2 meters is my rise. And my run, 1.5 again. So the same formula, slope is rise over run. This time my rise was 2 meters and my run was 1.5 seconds. Make sure you put your units in so you have the right units for speed. 2 divided by 1.5. So it's approximately, because we have to round, 1.33 meters per second. And then we need a little statement. Tyler walks away from the sensor at 1.33 meters per second. Or at a speed of is even nicer. All right. Two more examples to go for grade 9 math before your final practice. All right, question 4. The graph below shows the relationship between Rick's distance from a motion detector and the time he walks. So again, always check your axes first. The lower axis is the time in seconds. The vertical axis is the distance from the motion detector in meters, which means that down here is where your motion detector is. So Rick starts off 8 meters from the motion detector, okay? And we can see we've got a negative slope here, meaning he's getting closer and closer to the motion detector. So it says, which equation represents Rick's distance d from the motion detector based on time? So they all have that pattern, y equals mx plus b. And we know we're really good now at changing them. So instead of y, we've got d. So we can put d here. We know the slope's negative. So we can cross off b and d because they don't have negative slopes. So we have to figure out the slope number, which we'll do in a second. Instead of x, we have t. And our initial value is 8, so plus 8. And they both got plus 8, so it's between these two. So we have to figure out our slope, so we can draw in a rate triangle. It looks like it touches right there, but I know it touches here, so I'm going to make my rate triangle here. So my rise is from 4 to 8, so that's by 2s. So it's 4, but it's negative 4 meters. And my run is 10 seconds, so 2, 4, 6, 8, 10 seconds. So slope is rise over run, which is negative 4 meters over 10 seconds. Which is negative 0.4. So negative 4 divided by 10, negative 0.4. So then I want to know, is negative 2 over 5 negative 0.4? Or is negative 5 over 2 negative 0.4? You can test them each out and see which one matches to negative 0.4. So I'm going to try this one first. Negative 2 divided by 5 does give me negative 0.4, so it's that one. So it's got the rise over run. It's got the rise being negative 2 and the run being 5. You could also look on your chart and see if that works. If you go down 2, which is only 1 square because it goes by 2s, do you go over 5? Yes. You go over 2, 4, 5. So that makes sense. So you could have done it just by looking on your graph and seeing which slope made more sense as well, since it was multiple choice. If it wasn't multiple choice, you could calculate it, and that could have been your answer there for the equation with a decimal. All right, our last question. Maya's trip to school. Maya walks to her friend Kadim's house, which is halfway between her home and the school. So I'm feeling like this is going to be part A of the graph. Maya walks to her friend Kadim's house, which is halfway between her home and the school. They stay at Kadim's house for a few minutes until Maya remembers that she's forgotten her lunch. So this is part B, and she stopped there because it says she stays at Kadim's house. Maya runs back home to get her lunch. So this is going to be part C of the graph. She's going back towards home. When she gets home, her mother drives her to school so that she will not be late. This is part D. So there should be 4 parts to the graph. And then let's look at our graphs and see which one makes the most sense. So this is this is time in each of the graphs. And this is her distance from home in each of the graphs, distance from home. So Maya walks to her friend Kadim's house, which is halfway between her home and school. So she starts at her home. So in this case, she's starting from home because her distance from home is 0. And in this case, she's starting from home because her distance is 0. But over here in part C, she's not starting from home, she's starting away from home. So we can eliminate C as a possibility. And same thing with D, she's not starting at home, she's starting away from home. So we can eliminate this possibility as well. Okay, so Maya walks to her friend Kadim's house. So this is A, that makes sense. Then she stops at Kadim's house. And that makes sense for both graphs as well. She stops. Then she runs back home to get her lunch. So she gets all the way home. So in this case, she's getting further away from home. So that this one has to be eliminated. She's not running back home, she's getting further away from home. So in this case, you see she goes all the way back to 0, all the way back home. And then in part D, her mom drives her to school. That's why it's the steepest one, because she's driving instead of walking. So it's got to be B. Okay, so think of each little chunk of information as a part that's got to be on the graph and match up the parts that make sense to the statements for these. And remember, reading the axes and knowing what they represent is super important for this. Okay. All right, so I am going to minimize this and get everyone working together on our last practice. Oh, Xander, you joined us. Great. Okay, I'm just going to stop recording.